Hi, this is Dr. Kimberly Everson, and in this video I'm going to talk about the theory and background and how-tos in a theoretical sense, mathematical sense a little bit more of Oneway ANOVA. I have other videos where I show how to do Oneway ANOVA in various softwares, so you might check those out. Also, if you're interested more in learning how to conduct ANOVA in various softwares. First of all, let's talk about what it is. Oneway ANOVA is a method to compare the means of 3 or more groups at one time. And at one time, I mean it's a simultaneous test looking to see if any one of these 3 means differs from the others. It could be 4 groups, it could be 5 groups. You technically can do it with 2, but with 2 you can do a t-test, so you don't need to do an ANOVA. So typically it's done with 3 or more groups. There's a variety of other kinds of ANOVAs as well, but we're just going to look here in this video at a straightforward Oneway ANOVA, which just means I have 3 groups. I've measured something for all the members of each of the 3 groups, and I want to compare those means. Okay, so here's just some scenarios of when we might use it. For example, we have a school. They want to test the effectiveness of different teaching methods. They have 3 different teaching methods. They could have more, and they do a Oneway ANOVA to look at the test scores for the 3 groups. Another example might be growth of plants under different light conditions. We have 4 different lighting conditions, and we're measuring the growth. So we're going to look at the mean growth in those 4 groups. Another example might be customer satisfaction across different store locations. So we've got a variety of stores, maybe 3, maybe 5, maybe 8, and we're going to look at the satisfaction scores for those different stores and be comparing those stores to each other. When we do ANOVA, we want to look at some of our most important terms here. So we'll start off with that. First is the independent variable. That's the thing that is different across various groups. For example, maybe there's a different pill. I'm going to use pills as the illustration here. So we have a different pill across groups. It's the thing that's varied group to group. That's the independent variable. The dependent variable is the outcome we measure, the thing that we want to know whether the mean of is different. And this needs to be typically interval ratio. Okay, and so that's something that, you know, could be a test score. It could be an actual more physical measurement like weight or height, something like that. So it could be a sum score from a Likert scale or questionnaire, something that's basically interval ratio. Okay, and then we have groups. Here we have 3 pills representing our 3 groups, or different levels of our variable. And sometimes the groups are as simple as different racial or ethnic groups. Sometimes they are different treatments. Sometimes they're different locations. They can be anything where we're wanting to compare the mean for those 3. Okay? Now, one of the key things about analysis of variance, here the variance in there, analysis of variance, is we're looking at the variability. One of the key things that we're trying to do is look at the spread of the data, the variance in the data, within groups versus across group. Within group would be like those that all are getting the red pill. How much do the outcome measure, say we're measuring weight, how much does the weight vary? Let's say weight loss, that's probably something more logical. And they all got the red pill. In the red pill group, how much does the weight vary within, or the weight loss vary within the red pill group? That would be with the within group variance, and there would be within group within the other groups as well. Between groups is the variability across the groups. So if I have a mean weight loss for the red group, for the orange group, and the blue group, those 3 mean weight losses, I want to see how different from each other those 3 means are. So, and we compare the number 1 here to number 2 to do our statistical test to see whether really the difference between groups is is bigger than the difference within groups. That's what we're essentially looking at. So let's look at an example with some data here. We've got 3 groups. Maybe these are test scores. The bottom row here are the means. And you can see in this example that these are all pretty, all in the 70s. These are all mostly in the 80s or pretty close to that, the 50s. And so you can see there's a big jump between groups, okay? The mean between the 3 groups, if we look at the 3 group means, quite different from each other, okay? But over here, there's a lot of variability in the scores within groups, but we look at the 3 between group means, they're not as far apart from each other, and there's a lot of variability within groups. So in this particular case, there's actually a lot of within group variability. Look, this one goes from 59 to 89 compared to the variability between the group means. Okay, so this one is much more likely to come out as statistically significant when we do a one-way analysis of variance compared with this one, which is going to be maybe not. I haven't tested it. When we do our analysis of variance, I just want to show you the anatomy of the table that we're going to end up with, and then I'm going to go through on the next slide and talk about where these various numbers come from. Basically, we have this thing called sum of squares. Okay, it's basically the difference between individual values and mean values squared and added up. And we have a total sum of squares, which is really a measure of the amount of variability. If you threw everybody's score in a pot, all the groups, everybody in one pot, a measure of the amount of variability amongst that whole group, okay? And then we're going to have a measure of variability the within that's inside the groups, a measure of variability between the groups, which will be generally smaller, okay? We're going to have degrees of freedom associated with those. Mean squares, which are basically the sum of squares divided by the degrees of freedom. Okay, so I do the sum of squares divided by the degrees of freedom, get the mean square. And then an F statistic, which is really the mean square divided by the mean square. And from that, I get a p-value. You can see that this one here, this particular one, is not statistically significant. So no matter what software you're using, this was Stata software, I believe, you are going to get a table that looks something like this, okay? And it may or may not have this part on the bottom. One of the assumptions of analysis of variance is that the variances are approximately equal across the groups. So when if I look at here, is the variance for this group equal to the variance among these scores, equal to the variance among these scores, okay? Another way of saying is the standard deviation among these the same as these, okay? And so that's something that is one of the assumptions. We start off with a null hypothesis that they are equal, and we do this statistical test. Because it is non-significant, we can stay with our assumption that they're equal. They may not be, but we're going to stay with that assumption, okay? We don't have enough evidence to say they're not equal. If they're not equal, we may need to do an adjustment or other test, but we won't cover that in this particular video. Okay, so it may or may not automatically give you that test. Sometimes another tool, if you don't have that test, that's sometimes recommended is just to find the standard deviation of each of the groups, compare them, and if the biggest is more than double the smallest standard deviation for those 3 groups, then you worry about it. Okay, so in this case, at any rate, we don't worry about it, and it's not statistically significant in the end. And that's the basic data that we have. Now I'm going to go through the basic steps of the ANOVA. This slide has a lot of stuff on it, but we'll spend a little bit of time on it. You might want to take a picture of it if it's something that's helpful to you. The first thing you're going to do is your null hypothesis is always no difference among group means right there. Okay? And your alternative is at least one group mean is different. So if you have a statistically significant analysis of variance, all you know is at least one group is different from the others. You can look at the actual group means and make some initial hypotheses, and there are some ad hoc tests that can be done to test whether they're different. One thing that's sometimes recommended is just to find confidence intervals for the means for each of the groups and see if they overlap to see which ones are different from the others. But we won't be going into that level of detail in this particular video. Choose a significance level, typically 0.5, gather your data, and so forth, ensuring it meets assumptions. Now the assumptions again are going to be that equal variances, okay? The other assumption that's important is normally distributed data within each group. Very, very often with analysis of variance, your groups are too small for you to evaluate that, okay? So you're just going to make that assumption and go on with it unless you have a reason not to. If you look at the particular data, you typically want it to be fairly, if you were to do a little dot plot of this, to have it grouped, into the middle and not like extremely skewed. If, for example, I had this data in column C, but also 89, that's some extreme skewness there, and I'd worry about that, okay? But for the most part, you want to have no evidence that it's extremely non-normal is the idea here, okay? All right, so I have my data now. I've got this is my data in my columns. The first thing I'm going to calculate means. Okay, the first calculation, number 4 here. So I have a mean for group A, a mean for group B, a mean for group C, and I have an overall mean using all of the data. Now I should mention here briefly, my groups are equal in size. That's always ideal, but it is not a requirement, okay? If they're closer in size, it's better, but in this particular case, they are equal in size. Doesn't have to be. There's no like pairing up of this one, this one, this one. If there were, we'd be doing a more advanced procedure than one-way ANOVA. Okay, so I've got that calculated here. Got those various means here. Now what I'm going to do is I'm going to calculate the various sums of squares. And you don't have to do this by hand, your software does it, but I'm showing you how to do it so you understand what is going on here. I think it's helpful in understanding what ANOVA is all about, okay? What I basically do to get my total sum of squares is I take each value, so I'm going to take that 72, subtract the 70.6, square it, and that's that 1.96 right there. Then I do that with all of the values in the table. For each one of these values, I subtract this overall, the total sum of squares, 70.6, okay, square it. And that's what's given in this table here. So you can see like this 56 is farthest from that, so it's got huge numbers. So we've got some small, some are huge. And then all of these values are totaled or added up to give me my total squares, which is that 1997.6. That is basically a measure of the total amount of variability in the data set. It probably sounds familiar if you've ever calculated a variance by hand, really similar, except for we're not dividing by the number of observations or the number of observations minus 1 or anything like that when we're done. We're just taking that total, that 1997.6. Now, that total variability, we're going to now try to figure out how much of it is due to within group variability and how much is due to it between group variability. So that's what we're doing down here. And I'm going to show you the between group first, okay? What I basically do for the between groups is I take the group mean, subtract the overall mean. So I do that minus that, square it, okay? So 3.8 minus 0.6, I square that number, and then I multiply by the number of observations in that group. And remember, they don't have to be exactly equal, and that's where I get that 51.2. Okay, so it's just that difference between the group mean and the total mean, the overall mean, squared and multiplied by the number in the group. And then I'll do it for each group. So I do 82 minus the 70 squared and also multiply that by 5. And I do that here, okay? And 55 minus 70 square it multiply by 5, and I get that 1155, add all that up, and I get 1926. Okay, that 1926.4, that 2 is the degrees of freedom, it's not part of the sums of squares, is the amount of this that is due to differences between group A, B, and C. You can see it's most of it in this particular case, all right? And we could actually subtract to get this number down here, but I'm going to show you how we do it by hand anyway, okay? And I'll talk about the, well, I'll go ahead and do it now. It has 2 degrees of freedom because there are 3 groups. It's the number of groups minus 1 is the degrees of freedom associated with the between group sums of squares. And then I just do that number divided by 2 to get the mean square. So just the sum of squares divided by the degrees of freedom to get the mean square right there. Okay, so now let's do the within group. The within group is really just a matter of taking each observation, so the 72, subtracting its own mean. Okay, so 73.8, its own group mean. So 72 minus 73.8, so I get that 1.8, square it, and I get 3.24. And I do that for each of these values all the way down here. So the 78 minus 73.8 squared is at 17.64. And then for group B, I do it with its mean. So I get 81 minus 82 squared, put the value here, and so forth. And the same for C. Each of these subtracts its own mean, square it, put it in each of these. Okay? And so this gives me all the components. We add them all up. I get 71.2. And that is my within group sum of squares. It has 12 degrees of freedom. Now, how do I get 12 degrees of freedom? It's really just a matter of taking how many observations there are all together, 15 in this case. Okay, I've got 15 observations, and subtracting the number of groups, so 3. So I subtract 3. That leaves me with 12. These two numbers, the 2 and the 12, should add up to 1 less than the number of observations. Okay. So again, it's just number of observations minus number of groups. So I've got that. 12 degrees of freedom. Now I divide this 71 by 12 to get this number here. That is the mean square associated with this, okay? And those two numbers, I just do the top one divided by the bottom one to get this F statistic right there. And the degrees of freedom, an F statistic has 2 different degrees of freedom numbers. It's 2 and 12. Okay, so I just look up in a table or use software or whatever, and I say if I have, an F of 162 with 2 and 12 degrees of freedom, what's my p-value? And it's pretty much 0. I mean, it's 0 to 5 or 6 decimal places. And that's probably unsurprising because we can look at these 3 groups and see that they are very distinct, right? This one's not muddy at all. And I intentionally did this example this way so that it wouldn't be muddy. Very clear that that there's a clear difference between the 3 groups in terms of the scores that are being achieved in those 3 particular groups, and it's highly statistically significant. So that is how you do it. That is where those numbers come from, and for a one-way analysis of variance, and that's something you could just do by hand on a spreadsheet like I did, but I'm going to show you next just some software examples again. This is using Stata. You're welcome to use any software. You'll get the same thing. This is the example I just did by hand, and it has these same sums of squares that I found, the degrees of freedom I found, the 2 mean squares that I found by sum of square divided by degrees of freedom. The total is the same, okay? And I just divide this one by this one to get the F, and then it found the p-value for me. And again, it does that Bartlett's test to test of equal variances, and this was not significant, so I don't have to worry about whether the variances are unequal. That would be a more advanced procedure. Okay, so that's just one example. Second example, real briefly, I've got a score of some kind, and I've got 3 racial groups that I'm comparing. And you will see here I've got sums of squares, okay, and so forth. Now, you'll notice in this particular case, the sums of squares associated with between groups, that's where we compare each group mean to the overall mean, very small. And well, with the within groups is very big. This is the opposite of what happened last time. Okay, so last time we had most of the variance in the between groups. In this particular case, most of it is caught up in this within groups. So there's more variability within each racial group than across racial groups, and comparing the mean of one group to another. Okay, divide by the degrees of freedom. Again, there were 3 racial groups, so that's why the degrees of freedom is 2. And there were 117 individuals, so there's always 1 less in the total degrees of freedom. But I do this divided by that to get the mean square, this divided by that to get that mean square, and you see in this case, the top mean square is way smaller than the bottom one. Opposite of what we found last time, a huge mean square on top. It's just basically saying that the variability is mostly due to what's within a group, not between groups. And when I divide this by this, I get this F statistic, which will have 2 and 114 degrees of freedom. And that gives it that p-value, which is not statistically significant. And again, if you want to look at it down here, this p-value is the p-value for comparing that the variances are the same across groups, not statistically significant, so we don't have to worry about that again here. So that is Oneway ANOVA. You might look through my videos to see how to do it in your particular software. If you want the specific directions, this is a code you would use. If you're doing it in Stata, Oneway, and then you put the dependent variable first and then the independent variable, but other softwares, of course, will be done differently. You can look at it there. You can go to this website if you want to look to see if I have any books on ANOVA yet. As of the publishing time that I published this video, I do not.